For decades, software deployment suffered from a predictable friction. A developer builds an application that runs locally, but it crashes in production because the application code is tightly coupled to the specific underlying infrastructure of the machine. The traditional solution was the virtual machine. Here, we start with physical hardware, add an intermediary hypervisor, and then stack full distinct guest operating systems on top. Every application requires its own complete OS. This model creates a resource limit. Booting a complete secondary kernel for every single application consumes CPU and memory overhead that could be used for the application itself. This redundancy often caps the number of applications a single server can host at a single-digit number. Because hardware-level virtualization becomes a bottleneck at scale, the industry moved towards abstracting the operating system itself. Docker decouples the application from the hardware by leveraging the host machine's existing kernel. As the VM stack on the left fades, you can see the streamlined Docker architecture on the right. The guest OS layer is gone. This relies on a Linux kernel feature called namespaces. We're zooming into the host OS layer to see how the central kernel routes resources through isolated logical pipes. These create independent workspaces without replicating the operating system. Technically, a container is a specialized process running natively on the shared host kernel. To instantiate this process, we must configure three specific categories: the environment layers, the execution instructions, and the storage routing. Successful containerization requires moving past high-level abstractions to understand exactly how these three components interact mechanically with the host kernel. A Docker image is a template built from a stack of immutable layers. We start with a base OS plane. Each layer represents a file system delta. The runtime layer snaps onto the base, and the application code locks onto the runtime. This process is automated through a Docker file. Every instruction generates exactly one new immutable layer. The union file system flattens this vertical stack, compressing the planes into a single directory tree that the container navigates as a normal file system. Because these layers are strictly read-only, the execution environment is deterministic. This ensures the environment remains identical across every deployment. Immutability enables layer sharing. In this diagram, if two applications use the same base OS and runtime, the Docker daemon stores those foundations once and shares them. This mechanism reduces disk utilization and lowers network bandwidth required during image pulls. When a container is instantiated, Docker mounts a final, thin read-write layer on top of the stack. The container process treats this top layer like a normal hard drive, generating temporary cache and runtime logs directly into it. However, this layer is tied to the container's lifecycle. When the container stops, the read-write layer is destroyed, and any data stored there is lost. This leads us to the second pillar, execution. Every isolated process requires a startup instruction to boot. One method is the shell form. As seen on the left, the command passes through a shell validation box before reaching the binary. This creates a performance penalty and complicates clean shutdowns. The preferred method is the exec form. By using a JSON array, the command bypasses the shell entirely, drawing a direct line to the executable. This allows the Docker daemon to invoke the binary natively on the host kernel without the overhead of shell processing. Using the exec form ensures precise control over the process and eliminates hidden operational bottlenecks. Two Docker file directives deliver these instructions: CMD and entry point. The mechanical purpose of CMD is to provide default startup parameters for the container. CMD is easily overwritten. A command line argument physically knocks the default CMD block out of the pipeline, replacing it. Entry point is different. It acts as an immutable declaration. Arguments attach themselves to the end of the block as parameters, rather than replacing it. Because these arguments are appended, entry point locks the container's identity to a specific software function. The standard design is to combine them, lock the core binary with entry point, and provide overwritable flags with CMD. We must still address the data loss caused by the destruction of the ephemeral layer. When the container dissolves, everything in that top layer vanishes. Stateful data, such as production databases, must be routed to locations decoupled from the container's lifecycle. The primary path is the Docker volume. Here, data routes downward into an isolated storage zone managed by the Docker daemon. This provides native file performance while isolating the data. A second option is the bind mount. This routes data directly to an absolute path on the host file system. Bind mounts introduce security risks because non-Docker processes can alter the data. This breaks the isolation of the deployment, making them more suitable for local development than production. Finally, TMPFS routes data directly into the host machine's RAM for high-speed storage of temporary, sensitive data like authentication tokens. Data persistence is a routing decision that dictates the security, speed, and lifecycle of the application state. These components form the schematic of a production-ready container. The environment uses shared, immutable image layers mapped by the Union file system. Runtime behavior is locked via the exec form, ensuring direct communication with the kernel. Application state is preserved through explicit storage mounts. The container operates as an isolated host process, meticulously shaped by these three engineering choices. By mastering these mechanics, engineers can eliminate infrastructure overhead and design deterministic, scalable software deployments.